Okay, thank you.
Okay, Sarah Jordan, by the way. My name is very commonly mispronounced Jordan, so Jordan. So the work that I'm going to present today is some work ongoing with two of my collaborators, Xingyu Xu, who is Ben Hobbs' PhD student, who is now a postdoc, and also with Professor Ben Hobbs at Johns Hopkins University. I'm with the School for Advanced International Study, and they're with the Whiting School of Engineering. So we're going to take a step back now. I'm just going to get everybody thinking a little bit about life cycle assessment to understand the basis of this project. Life cycle assessment is a cradle degree of assessment. I'm sure many of you have heard about it before and even undertaken them. One of the big challenges to life cycle assessment studies, however, is that they generally entail snapshots in time and space. And as we all know, energy systems don't operate in that way. They are dynamic systems that interact on an hourly and even sub-hourly basis, and right now we've even experienced a large energy transition. So what I'm going to be talking about is within life cycle assessment how we can start to consider some of these very important spatial aspects of the energy system, and in particular and also temporal aspects, and in particular to get a good idea for how grid textures can influence emissions outcomes. I'm not going to spend too much time on this other than saying life cycle assessment is an internationally standardized method, and that primarily stems from the fact that it was originally used in many cases to promote specific products, but it's often used in the scholarly space to advance materials in this way to get a better idea of the way that our energy systems work. What I'm going to be looking at is specific to the energy system. How we generally do life cycle assessments of energy or of electricity is that we look at singular technology. So I'll do a life cycle assessment of natural gas, and they don't typically look at the grid scale. So if we start to think about energy transitions, how can we account for the interactions among different generators on the grid? So as a result, they typically look at these generation or annual averages, looking at different proportions of electricity. And so what we are going to focus on here is looking at how to account for the dynamic interactions amongst generators on the grid. So the purpose here is to develop a life cycle approach to account for renewable systems integration, rather than looking at singular technologies. How we went about doing this is, in essence, an integration of optimization models, and that enabled a way to estimate the life cycle grid emissions from a regional perspective. We took into account plant-level inputs and how dynamic interactions occurred across different changes. Subtle changes in the grid can change emissions outcome under different renewable storage and carbon pricing options, and looking at different configurations of these. And what's different than just looking at the emissions of the electricity generators is that we also took into account the upstream fuel supply as well as the downstream generation, thus enabling a more comprehensive emissions estimate. So what my collaborators have spent the past couple of years doing is looking at a particular region, the Western Electricity Coordinating Council. So this encompasses the Western interconnection. So it's a large area of North America, and in essence the western half. It's part or all of 14 states that includes British Columbia and Alberta and a small slice of northern Mexico. So it's approximately 265 gigawatts of generation capacity. And it's governed by the Western Electricity Coordinating Council, and their purpose is to maintain reliable power, assure an open and non-discriminatory access to transmission, and also provide a forum to resolve disputes. So my collaborators, and I became very interested in this work due to the limitations in life cycle assessment, have developed a model that looks at how to co-optimize the system. So if we're going to look into the future and look at different grid configurations in the future, how can we necessarily go about doing that from an optimized perspective, given the fact that we could have a variety of different potential future outcomes? So they've developed the Johns Hopkins Stochastic Multi-Stage Integration Network Expansion Model, which in essence looks at this co-optimized model of transmission and generation planning. So what I've looked at in this particular paper is how to integrate their approach with life cycle assessment to get an idea of the grid scale life cycle emissions benefits. So what we did was integrate both. What I did was integrate both their work and life cycle assessment by looking at future scenarios of storage and carbon pricing, and it includes details of transmission and generation planning, so how these particular parts of the system are going to interact with each other. And also the upstream emissions. And this gives you a quick look at how the multi-stage system works. So looking at initial decisions, so today's choices, and then 10 years out where you have a specific probability to land on a certain event, and then another stage which looks out into 2034. So we expand out from looking at just generation. So this model gives you an idea for the system that we're looking at. So these are the power plant operations right here. So it takes into account the upstream from the power plant construction, but also the upstream fuel supply. So mining, processing, storage, transport of coal, of natural gas, uranium, et cetera. So it's the systems model. Wind, so the idea is to account for the entire grid, which is in this particular case primarily actually renewables and oil and gas. But the idea is then you add in storage operations. We at this point haven't included the upstream manufacturing associated with the storage, but it includes the interactions between them. Although the upstream manufacturing and the storage is actually quite small at this point, but we are going to include it later for completeness. In accounting for the upstream fuel supply, right now we're at early stages, so we haven't developed a full upstream supply configuration of what that entire region looks like. So what I did to start off to get an idea for how these systems can be integrated, these modeling approaches can be integrated together, is to take a look at the National Renewable Energy Laboratory's harmonization study. So what has been found in previous life cycle assessments is that you can choose a large number of different systems boundaries as well as input assumptions. So what the National Renewable Energy Laboratory did was they did a systematic review of all existing estimates, so of life cycle assessments between 1970s and 2010. And apologies for some of this right here. This is Mac compatible. I use the PC, so if some of the writing is missing, that's why. At any rate, so they compiled all of these and then made the modeling or life cycle assumptions consistent. So for example, making consistent by the assumption of the electricity efficiency of the particular generation technologies. And that's called a harmonization process. And then through doing that, they can reduce the variability across all of the existing life cycle assessments and really clarify what the central tendency is for these life cycle assessments. But what it does is they've done is provide a database of all existing estimates, okay, from which one can work with. So in order to integrate both approaches, I used the co-optimization model. So what this does is it simulates market adjustments in response to hypothetical storage, grid, and renewable configurations. I used to develop a proof of concept of how we can go about integrating both models. I combined this with NREL's harmonization data. By doing so, I applied distributions to their information and then ran a Monte Carlo simulation. So using Oracle Crystal Ball, 10,000 repetition sampling from the distributions of the existing LCA studies to bound the uncertainty of what the potential upstream emissions can look like. I'll get into that a little bit more. The scenarios include different configurations of the additions of 1,200 megawatts of pumped hydro in Oregon, addition of 1,200 of compressed air energy storage, battery energy storage systems in California, wind capacity, and then a number of different configurations of carbon pricing. So that would be none, $20 per ton of carbon, $58 per ton of carbon dioxide, and then 100. So to give you an idea of all the different scenarios that were looked at, this is a number of them, and this is what in essence we turned on and off for each of the different scenarios. So we looked at all the different configurations of each. and then including the different storage scenarios. And these are in specific locations of the grid, so it enables you to get a good idea for how specific locations can enable different emissions outcomes. And in order to make this compatible with LCA, you can't just add, well, you could, but in order to account for the subtle differences of each of the electricity generators, I, in essence, adjusted the emissions factors from the NREL study according to the heat rate of the individual generation units. So for each of the different generation units that are accounted for within the optimization model, I adjusted them for the specific efficiency, and then use the unit generation output for 4 representative days of the year, which were aggregated in terms of the emissions or the generation over a year, then applied the heat rate, and then characterized the distributions of each of the NREL data, which were I then truncated by the highest and lowest points available in the data set. So in some cases, the data were scarce. So for geothermal, for example, then you use then apply a normal distribution in the absence of enough to characterize an actual distribution. So these are the results of this study. So this doesn't appear to be much right now, but we'll take a larger look at this shortly. So what this is these are all of the scenarios, and these are the differences in the technologies, okay? So this is these are the gas options, coal, and then nuclear, and then the renewable options here. And then this is the same for each of the different scenarios that I just showed, and we're going to take a bit of a closer look at those scenarios now. So what we ended up finding from looking at the different configurations is that carbon price actually appears to be a large driver in the behavior of the power plants, which we've seen in a number of the different studies today. But just to give you an idea, this is the base case, so that's assuming nothing happens. So this is the base case, so assuming that there are no additions of any new technologies or application of a carbon price. And then in this case, you have applications of storage as well, both types of storage, as well as the wind under a $20 a ton of carbon price, and then $58 a ton of carbon price, and $100 per ton of carbon dioxide price. And then what you can see is subtle differences among the technologies that are applied, but really driving different behavior from the carbon prices. How am I doing for time?
It's like 3 minutes.
3 minutes? Okay, that's good. I think I can work with that. So this is just a comparison of the emissions results from the optimization model in comparison to when you couple it with life cycle assessment. So what we found was that there is a 37% decrease in life cycle emissions from the base case. So that means that these very small, relatively small storage additions, storage and renewable capacity additions, can make a large difference depending on where they're placed within the system, okay? The upstream displacement is captured in the LCA results, and because it's a relatively clean grid anyways, it adds an additional you can see the additional emissions benefit, but there's an up to, depending on the technology configuration, up to 45% increase in those emissions, because what was previously 0 emissions now has an emission, and in addition to the upstream. So it's actually quite large in this case. But still the 37% decrease from the no emissions case, or sorry, from the base case, apology. Aside from the carbon price, which was found to be the biggest driver in behavior on the grid, the new wind capacity has the largest benefit if it's added, but even larger when you add the storage along with it. Okay? So the conclusions from this study is that what we found is that grid level emissions have subtle differences based on the configurations of storage and wind. Carbon pricing has a substantial impact on the behavior of the generation unit, so it can result in more substantial emissions reduction, and that's through lower burning of fossil fuels in plants. what other areas to think about is at this point it's only the grid emissions that experience the carbon price, so we haven't checked to see how that might affect behavior across the entire economy within the upstream. And in addition, it's unclear at this point how developing a full spatially resolved upstream inventory might influence the results. But what we really want to emphasize is that detailed evaluations of grid impacts of storage technologies, if you're looking, and renewable technologies, can uncover more realistic estimates of the life cycle trade-offs from planning decisions. So instead of just taking a look at singular technologies, looking at the interactions can uncover differences that really matter. Just a few areas of additional interest, clearly improving what we've done here so far, better integrating LCA into optimization models, as well as improvements in upstream fuel analysis and looking to make that more spatial and temporally resolved. And an area that I think is really important moving forward, and there's been a number of discussions of ramp ups and ramp downs, but taking a look into the trade-offs of modeling, better improvements in modeling of heat rates, because at this point, each of the individual units has a static heat rate. So the idea is to look at making that more dynamic and interacting better with the changes on the grid. So I look forward to your questions. Hopefully there's enough time for some.
Questions?
So you mentioned there's some critical place if you add storage and make a difference. So could you clarify what you mean critical place?
So it matters on where you put it. So clearly if you put storage in an area that might have additional transmission constraints in particular areas, so we looked at for example, battery storage in California, you might find that in particular locations that due to the way that it interacts with the rest of the grid, there could be additional benefits rather than putting it in an area that would be less constrained. Could somebody, is there an additional mic for the audience? It's a little bit difficult to hear. Thanks. This one? Yeah?
So Paolo Gabrielli from ETH Zurich. Can you? The comparison between case with and without life cycle assessment is the second and the second to last lines. So because if you go to the second to last line that you have decreased with respect to this NNN scenario.
Oh yeah, so this is actually the decrease from when you do nothing at 58 carbon price, and this is a decrease from when you do nothing, add nothing at a 0 price. And this is the difference increase from the optimization model.
But then, and the second line, so what you do if you do nothing but not including LCA.
This is just doing the optimization model.
And then, so the different, when you include LCA, second to last line, so in the first column, you have a higher decrease. In the second, you have a lower decrease, and I don't really know how to put them in perspective between the two.
Oh, so this is if you're decreasing from using LCA. So this would mean in this generation scenario where you have yes to all the configurations and a $58 price, using LCA results, looking at the price when you do nothing, it's 4.4. If you have just using the optimization results, then it would decrease by, from the non-optimization results, it decreases by negative 3.9.
All right.
So optimization, LCA to LCA.
Yeah.
Make
Right.
sense?
Yeah.
Does that clarify? I think there was one other question, but I don't know if we have time.
Yeah, quick one.
So just from my understanding, so the carbon life cycle system go into the optimization model and it takes those into account in its build decisions. Is that correct?
At this point, what we've done, because it's early stages, at this point what we've done is we've run the co-optimization, which generates hourly dispatch for 4 representative days, which I then took and then adjusted each of the individual units and applied the efficiency of the individual units to get an idea for what the upstream impacts can look like but each of those individual units are running based on the assumed or the optimized interactions with the other units on the grids in this future scenario. Make sense?
Okay, great. Let's thank Sarah once more. Then we're lagging a little bit behind here because of some